Okay, so we will start the session. So this is all about Boolean logic and digital circuits. We'll try to complete as much as possible. So more than completing the session, I want to do some fast review questions as well. Okay, right. So therefore, let's straight away move on to the topics. Right. Right. So this is what we are supposed to do in this particular maybe roughly 2 to 3 hour session. So we will be discussing part one Boolean logic. Hopefully, if we have time, the digital circuit components. Okay. So part one, we will be discussing what is mean by logic, why we are learning Boolean logic, propositions, logic operators, Boolean algebraic rules, universal gates, and in the session 2, or actually we are going to cover the session 2 as much as possible today itself. Uh, Digital circuit component, designing digital circuit components, that is designing digital circuits for given input output combinations, either SOP or POS approach, designing the simplest possible SOP or POS using Boolean algebraic rules or using Carnot map. Then some useful digital circuit components like adders, decoders, encoders, multiplexers, flip-flops, etc. And finally, how those digital components are used by the computer for doing different tasks. Okay, so we try to cover as much as possible. But for the exam, most of your questions are from this part. Okay, the first part. Very few questions from second part. So therefore, we will be concentrating a little bit more on try to understand the concepts. So once you understand the concepts, it's very easy. Okay, right. Right. So I'm going to start from very beginning, basics, but I will be doing it a little bit faster. Okay. Right. So let's start with what is mean by Boolean logic. Or let's start with what is mean by logic. Right. So the logic is the formal science of reasoning. So when we reason out something, we have to use logic. By the way, this topic is related to your semester 2 math subject as well. You have the sets and logic. So those are the biggest subject, two topics where you get the bulk of the questions. So this session you will help doing that those two topics in the maths as well. Okay, so therefore you don't take this as a light. Don't take this lightly. This is very critical topic for any information technology or IT professional. Okay, right. So because IT is all about logic, right? When you are writing a program, when you are designing a database, right? Internally, everything it is logic. So logic is our main subject. Okay, right. So logic is the formal science of reasoning. When we want to reason out something, we use logic, right? So we use logic. Or sometimes when we want to take some decisions, we have to use logic. Okay, so that is why we are interested in logic. Of course, we know that computer is capable of processing logic, right? Right. So use of logic. Of course, we can use logic day-to-day life, right? For example, when you are crossing the road, you have to use a logic, right? Sometimes when you get up in the morning, you are using some logics, right? So for example, if you want to cross the road, right? So you use a logic, right? So that is you will check whether there are any vehicles from the left side, are there any vehicles from the right side. If there are no vehicles from left side, and if there are no vehicles from right side, you cross. So that is a logic, right? That is a logic. And there you use the AND operator, right? There you use the AND operator, right? So likewise we use logic day-to-day life as well. For example, when you get up in the morning, right? Get up in the morning, right? So sometimes when you get up in the morning, all of a sudden you don't remember what day it is today, right? So if you just remember it and if you just going for work, you are working somewhere, maybe if it is weekday, I will immediately get up. If it is not, I will just sleep another maybe just 1 more hour, whatever. So that is also logic, right? So everywhere, right, you are using logic in your life. Then in the science, we use logic because science is a logical subject, right? Even in philosophy we use logic, and in mathematics we use logic. So mathematics is 100% logic, right? So when you add in numbers, say 55 and 72, so say 55 and 72, 5 plus 2 is 7, then 5 plus 7 is 12. So now we are using another logic. So 12 is bigger than 10, therefore we just write 2 and take the other one here. So that is logic, right? If the value is less than 10, you just write it. If it is greater than 10, you have to bring forward, right? So that is also logic. So maths is all about logic, right? So therefore don't think that maths and logic are two different things. Yeah, maths and logic are somewhat different, but maths is 100% based on logic. Okay, so then computing, right? Information technology, the way computer works, it's based on logic, right? So the computer hardware like processor, memory, all those devices work on logic. When you are writing programs, basically we are writing the logic, business logic. When you are designing a database, right? So we have to design it in a particular using some logical concepts like normalization and stuff like that, right? When it comes to networking, so all those routing and other things are happen based on certain logic, right? So certain logic using IP addresses, etc. So therefore, if you know logic, right? If you know your logic, your day-to-day life is going to be really productive, right? If, especially if you are a IT professional, your career is going to be really interesting, right? Therefore, for IT professional or for anyone, logic is a really critical subject, right? And we know that we say that we are the most intelligent people species in the world or the earth. Why? We can process logic more than any species in the earth. So that is why we have dominated the world, right? As humans, right? As humans, we have dominated. Why? We can process logic more than other animals. Okay, so same thing, right? Same thing. Right. So therefore, if you want to have a really good life, right, productive life, quality life, you must be really good at logic, right? So forget about the exams. This is life critical subject. Okay, right. Right. So then there are different type of logic, right? So what we are going to cover is the Boolean logic, because Boolean logic is the sort of the most formal logic. So that is the most sort of a formal logic that we used in science, in engineering, maths, etc. So therefore, we are going to cover in this particular session. Actually, we are going to cover only Boolean logic, right? So Boolean logic means two-state logic. Two-state logic means when you have sort of a statement or proposition, it must evaluate to be either true or false. So it can't be both, though we can't say it can be true or false. No, it must be definitely true, otherwise it must be definitely false. In that kind of situations, we say that we can apply Boolean logic. Okay, so that is the most widely used formal logic approach, right? In day-to-day life, science, maths, we use Boolean logic. Then there are some other type of logic as well, like fuzzy logic, things like, especially when it comes to artificial intelligence and stuff like that. We are interested in fuzzy logic as well. There we use concepts like probability, statistic, and those things, and come up with some decisions, right? So that is called fuzzy logic. And there is something called four-state logic as well, which is also fuzzy logic. So in four-state logic, we assume that there can be statements which can be true, which can be false, which can be both true and false, right? Which is neither true nor false. So if you think like that, then we say that it is sort of a fuzzy logic, right? So it is sort of a fuzzy logic. Not only in philosophy, right? So we are now using some sort of fuzzy logic in even physics subject like physics as well, like quantum mechanisms, etc. Right? So quantum superpositions, etc. So we are using sort of a four-state logic as well, right? So but what we are going to cover here is the Boolean logic, right? Boolean logic, right? So from this point onward, we will be discussing Boolean logic. Okay. So why we call it Boolean? So Boolean is a mathematician's name who worked on a lot of logic area. So therefore, people using this term Boolean logic. Okay, so Boolean means just a person's name, right? So for you, Boolean logic means two-state logic, right? Two-state logic. Your propositions must be either true or it must be false, right? So you can't have in between, so neither, right? So when it comes to Boolean logic, right? So we call it two-state logic, right? So the basic building block of Boolean logic is the concept called proposition, right? Concept called proposition, right? So you have learned what is mean by proposition under your math subject as well, right? So that is how you start your math logic subject topic, right? So proposition is a statement, right? A statement which must be either true or it must be, sorry, there's a small printing mistake here, it must be false. Okay, so I just hurriedly prepare this one. So statement which is either true or if it is false, then we say it is a proposition, right? So it must be definitely you must be able to say it is true, or definitely you must be able to false. It can't be something like it can be true or false, it can be neither true nor false. No. So by looking at the statement, you must be able to say definitely it is true, right? Or definitely it is false. So that kind of statements we are talking, we are considering when it comes to Boolean logic. Okay, when it comes to Boolean logic. For example, if someone says 2 is greater than 5, so that is a proposition because we know that that statement is false, right? If the statement is definitely false, that is a proposition, right? Someone will say sun rises in the east. We know that yes, sun rises in the east, right? So therefore, it's a true proposition, right? True proposition, right? For example, someone will say if you buy more than 10,000 worth goods, you will get 10% discount. Now, if you have bought say 15,000 worth of stuff, now definitely you must get this discount, right? So that is also Boolean logic, right? So we have to write this kind of logic in when we are doing programming, etc., right? Programming, etc. So those are basically what we write is in if else conditions, switches. What we write is Boolean logic. Okay, right. Right. So when it comes to propositions, we can subdivide it in two. Right. So what we can identify is simple propositions or atomic propositions and compound propositions. Right. Compound propositions. We know that proposition is a statement which is always true or which is always false. A compound proposition is combination of propositions. Right. Combinations of propositions. That connection has to be done using a logic operator. Right. Logic operator. So it's a combination of propositions, right? Combination of other propositions, and that combination must be done using a logic operator. So the logic operators are operators like not, right, and, or, XO, etc. Just like in arithmetic, we have addition, subtraction, multiplication, division, right? In logic, Boolean logic, again we have operators and we call them the AND logic, OR logic, NOT logic, XOR logic, etc. Right? So by using those logic operators, just like we can say 5 into 2 is 10, we can have two statements, propositions, and now we can combine using not by these things by something like AND, OR, NOT, etc. So this is an example. 5 is greater than 2 and 5 is even number, right? So we know that 5 is greater than 2 is a proportion, 5 is an even number is a proportion, right? So 5 is greater than 2 is a true proportions, 5 is an even number is false proportions. Now we have combined it using and using your logic knowledge you will know that true and false is false. Therefore this entire statement is also a proposition which is a compound proposition, and it is a false proposition, right? So likewise when you combine atomic propositions using logic operators, what you get is also a proposition, and we call that big proposition as a compound proposition. So that is where the concept called logic operators come, right? Otherwise you don't know where this logic operators comes. Why we have logic operators? We can use logic operators to combine propositions and we create bigger or compound propositions. Okay, right? So that is where the concept called logic operators comes to the usage. Okay, so if you have any questions you can ask anytime, right? If I know it I will definitely explain it, otherwise I will say okay, I also have some doubts. Right, so these are the basic operators, logic operators when it comes to Boolean logic, two-state logic, the NOT operator, AND operator, O operator, and XO operator. Right, so there are some deviations or the derived operators, but these are the basic operators. Okay, right. So when it comes to understanding Boolean algebra or the Boolean logic, we can approach it in different way. But one of the famous approach is approach your Boolean logic through sets, right? So because sometimes understanding logic is little bit tough because it's a concept, right? It's a conceptual things. But sets is a mathematical concept where we can visualize things, right? So therefore once you understand sets, you will see that there is a sort of a one-to-one mapping between the theory of sets and the Boolean logic. So that is why in your semester 2 maths also you have this sets followed by logic, right? Because sets and Boolean logics are really related to two related concepts. Okay, of course sets is related to so many other things as well, like relational algebra in your database, etc. But one way of looking at Boolean logic is the use of sets, because sets you can visualize. Logic is a sort of a conceptual thing. So when you can visualize it, you are in a better position to understand the concepts. Okay, so that is why we are going to just briefly look at sets. Then we are coming back to the logic. Okay, right. So when it comes to set, a set is a well-defined collection of elements with following properties. What are those properties? No duplicate elements must be there, right? So that means same element can't be duplicated. If that is the case, it is not a set, right? No duplicate elements, right? And then the order must not be important. So if someone says that order is important, that is not a set, right? That is not a set. Order must not be important, right? For example, this is a set. Say 2, 5, 8 is a set, but this is not a set. 2, 5, 8, 5 is not a set because the same element is there. And also, if someone says order is important, if someone says after 2 it must be 5, then it must be 8, then it is not a set, right? So that is not a set. Order must not be important. Okay, so that is how you understand a set. Okay, so of course you have learned sets in your O level as well, but you have to look at those things in a very serious manner now, right? So simple concept, but you have to look at those in a serious manner, right? So it's a collection of elements with no duplicates and order must not be important, right? Right. So then we have two special type of sets called universal set and null set. Okay, so I will explain you that later. The universal set is mapped to one concept in the Boolean algebra. The empty set is going to map to another concept. So that is why we are learning these things, right? So we are not going to learn this just like the O-level students. No, we are going to learn this with some serious objectives. Okay, right. So universal set means a set of total interested context, right? As total interested context is called the universal set. For example, uh, so if you have a set, say A, maybe it has vowels A, E, I, O, U, etc. Now the universal set can be depends on the way you look at it or what is your big context is, right? If you are just looking at a language like English, your universal set will be the characters in the alphabet where A to Z, right? So that is possible one possibility of universal set, right? So likewise, if you take a set where say A is student at say some institute following bit, right? So that is your A. Then your universal set can be there are so many possibilities. It depends on the way you look at it. For example, one possibility of universal set is the student in that particular institute, because this is student following with that particular institute. So one possibility is student following any courses in that institute. Another possibility is if it is something to do with the UCSC or something like that, they will say if this is student following with at particular X institute, the universal set is student following with, right? Even if you go to the education ministry or something, they will say universal set is a student following IT in Sri Lanka. So likewise, E depends on the way you look at it, right? So that is why we say a set is a universal set is the set of total interested context, and it depends on the your context, right? Your context. But once you define your context, we don't consider anything beyond that. We don't consider anything beyond that. That is outside our context. Okay, but that context totally depends on you, your point of view, your interest. That is why we say interested context. Okay, right. So the next concept is empty set, right? Empty set. So when empty set means a set containing no elements, right? No elements. If we can think of a concept, right? Think of a concept, but when you think about it, you don't find any elements. Then we say it's an empty set, right? It's an empty set. A set having no elements is called a empty set. So that still you have to come up with a well-defined concept, right? Well-defined concept, but there must not be any elements. For example, I can say. X is a number or maybe negative number bigger than 100, right? So we know that there are no negative numbers bigger than 100. So as a concept, I can say it's a number bigger than 100. Now definitely it's going to be a empty set or null set. Okay, right? So those are very straightforward. I know that those are very straightforward, but you have to be very serious looking at those simple concepts. Okay, so looking at those simple concepts, right? So then after sometimes the logic is going to be really simple topic, right? If you are not looking at these things seriously, yes, the logic is going to be somewhat difficult topic, right? Right. So now let's look at the set operations, right? So still we are talking about the set operations, right? Not we are still not moving to the logic or the Boolean logic. So when it comes to set, so think of this as sort of a small revision on your math subject as well. So when it comes to set, there are well-defined operations we are talking about, right? So the intersection, the union, the complement, the set difference, and the if you want, you can think of XO as well, right? XO as well. Usually we don't talk about XO when it comes to set, but if you want, yes, you can define that concept in the set operations itself. Okay, right. Now let's take one by one. So what is mean by intersection? So intersection means so you must be able to formally define those things, right? Formally define those things. Uh, so intersection means visually, right? If you look at it visually, intersection means the common area, right? Intersection means the common area, right? So how do we define it? So we say that A intersection B is X such that X is a member of A and X is a member of B, right? If there's a element X such that which is also member of A as well as member of B, we say that that member is part of the A intersection B, right? Now you can see that when we talk about intersection, we have to use the logical concept called AND, right? Logical concept called AND. If it belongs to both A and B, only we say that it is intersection, right? Right. So it has to belong to both A and B, then we say it is intersection. Now you will see that intersection and operator has a direct connection, right? Intersection and has a direct connection. Okay. Now let's look into the next set operator, which is union. So when it comes to union, we say that A union B we can define in such a way X such that X is a member of A or X is a member of B. If that happens, or if we consider that particular scenario, we can say that in mathematical sense, we can say that that is A union B, right? That is A union B, right? So So that is how you define union, right? That is how you define union. Now you must see that the union and O operator has a direct connection, right? So if something belong to A, O, if something belong to B, we say that that area is A union B. A union B. Now let's look at the next set operation, that is complement. We say that A complement is this particular area. So that is the elements which are belong to E or the universal set, right, but not belong to A. Then we say that that is A minus B. A minus B. Okay. So that is area which belong to A but not belong to B is called set difference or the A minus B, right? So we are going to use all those things in logic as well. Now again you can see we are using the AND logic, right? We are using the AND logic and also we are using the NOT logic, right? So here we are using the NOT logic, here we are using the AND logic, okay? Right, now let's look at the XO. Now you may not have used XO logic, right, usually when you are doing sets, but you can look at XO logic from the set itself, right? From the set itself. XO logic means something which is belong to A but not belong to B, or something belong to B but not belong to A. So that means A minus B or B minus A, right? A minus B or B minus A, we can say that it is exology, right? We can say that it is exology. So that is why later we will say that we can say A, right? So just 1 minute. So later we will say that in logic we can say that A exclusive of B can be written as A B bar plus A bar B, right? So that is how these things comes, right? So A B bar means belong to A and not belong to B, or so I can just write it like B A bar belong to A and not belong to A. So this is belong to A and not belong to B, or this area is belong to B but not belong to A. So that is how we get A exclusive B as A B bar plus B A bar, right? So you have to don't memorize these things. Once you got these concepts, right, once you understand these concepts, you are not going to memorize any of these things, right? So just naturally you are going to remember these things, okay? So that is why we are talking these things using sets, because set is something we can easily understand, right? We can easily understand because we can visualize those things, right? We can visualize those things. So if unless you have very good understanding about what is AND, what is O, what is XO, what is not, your life is going to be really really tough, right? And not only your IT professional life, even your day-to-day life, okay, right? So now you must know exactly what is mean by XO, that is belong to A but not belong to B, or it must be belong to B but not belong to A. So then only we say that it is exclusive O, right? Right. So now we have covered the basic set operations, intersection, union, complement, relative complement, and we just took another operations. We just call it XO. We borrowed that concept from the logic. Right. Now let's look at some algebra of sets. Right. Algebra of sets. So algebra of sets means there are some rules that we can use when you are working with set operations, right? So those rules you have to remember in your because we are doing both semester 1 and semester 2 in within very few weeks time, right? So in your semester 2 you have the sets, right? So there you will get at least 6-7 questions in your maths paper. So therefore this is important for your maths as well, right? Right. So when it comes to sets, we can identify few well-defined rules. So those rules, I am not saying you have to memorize it. Actually, if you appreciate those things, if you really like the subject called logic, you are going to naturally remember those things, because you know that these things are really, really naturally correct things. So therefore, you are going to just naturally remember those things, and those are very simple as well, okay, right? So the first rule when it comes to algebra of set is complement of complement is the same set. So that is again common sense. When I say common sense, that is common simple logic, right? Common simple logic. So when you take, so sorry, right? When you take something like A, right? When you take something like A, not belong to A is this area, because we can't go beyond D. That is A complement. Then A complement's complement means again not belong to this area but belong to E. So again that becomes your A. So therefore we can say that complement of complement is A. Right? So that is, if you think about it, right? If you think about it, you will feel like yes, that is the case. Right? So now let's look at the second one. So these things you can use in your sets subjects, okay, math subject as well. The next one says E complement is 5. So that is again you have to think about it. Now what is E? E is our total context. So we don't care or we are not interested outside this. Right? So remember the definition of E? The total interested context. We are not interested anything beyond that. So in that case, what is E complement? So if E is our total interested context, we are not interested anything beyond that. So in that case, E complement is going to be 5 because there's nothing we are interested beyond E. So that means it must not belong to E but within E. So there can't be anything like that because that is our E, right? So then phi complement. So what is phi complement? So phi complement is E. So how do you understand that? So in that kind of a situation, we can rather than just looking at this value, we can just look at the approximate value, or the we can just try to reach to that thing. For example, if you have A, we know that A complement is this area. Right? We know that A complement is this area, right? But what we need is not A complement. What we need is phi complement. But if you just make A smaller and smaller, smaller and smaller, what will happen? This not belong to A going to be bigger and bigger. And when A becomes nothing, so that is what is known as empty set. When A becomes nothing, we have shaded everywhere within our context. So therefore, we can logically we can say phi complement is E, right? Phi complement is E. So that is where you start thinking logically, right? As a logic, right? As a logic, if A complement is whatever outside A, when A is getting smaller and smaller, this area is getting bigger and bigger, and it is getting close and close to the E. And when this vanish means now it is 5. Now everything has been shaded. So therefore now we can say phi complement is C, right? So we are going to use all those things in logic, all those things in logic, okay? But we are going to first understand those things using sets, because sets, understanding set is very easy for us, okay? Right. So then we have A intersection B is same as B intersection A. That is again common sense. Common sense. It doesn't matter from where you start. A intersection B means it must be both belong to both A and B. So ultimately, what you get is this area. This area. So therefore, whether you start from A side or B side, it's going to be the same. So therefore, we can safely say A intersection B is same as B intersection A. Just like we say in arithmetic, 5 plus 8 is same as 8 plus 5. Right? 8 plus 5. So that is something like that, and this is not going to work everywhere, right? For example, you can't say 5 minus 8 is same as 8 minus 5, right? So that is different thing, right? So but just like 5 plus 8 is same as 8 plus 5, we can say A intersection B is same as B intersection A. Okay, A intersection B is same as B intersection A. So similarly, we can say A union B is same as B union A, right? So again, if you draw it, you will see that ultimately entire thing is going to be shaded, right? So therefore, that is also correct. Now we are gradually understanding, right, some relations which will belong to the sets, because these things are going to have one-to-one mapping in the logic. Next one is A intersection B intersection C is same as A intersection B intersection. That means it doesn't matter which one you are going to do the intersection first, because ultimately it's going to be the middle area, right? This middle area. So this middle area. So therefore it doesn't matter whether you first do these two and next one, or first you do these two and next one. Okay. So it doesn't matter which one you do first. Therefore we can say the brackets are not important. So same thing there for the union, right? So the next one is if you have the intersection and union, right? It's something like in maths you have a multiplication and addition, no subtraction, right? So you can just say it is 5 into 5 plus 5 into 2. Similarly, in sets we can say A intersection B union C is, now this is different from this one, that is A intersection B union A intersection C, right? Similarly, if it is union here, it is A union B intersection A union C. If you have any doubts on this, what we have to do is draw the left hand side in a Venn diagram and see which area you get. Draw the right hand side and you will see that you are shading same area. Same area. That means that is correct. That is correct. So that is how you get it. Okay. So then we have another operation. We call it De Morgan law. That is A intersection B's complement is A complement union B complement. Right. Similarly, A union B's complement is A complement intersection B complement, right? So that is also very important. But now if you want, you can just draw it and see by yourself, right? Draw it and see by yourself. For example, if you take this one, right? A union B's complement means, so just take the A union B. We know that A union B is this area, right? So this area, so entire area, so its complement is whatever outside this, whatever outside this. Now look at this one. So if it is also this area, we can say this is correct. Right? Now let's look at this one. That is A complement. So A complement means everything other than A. Everything other than A. That is this entire area. Then we have the B complement. That is everything other than B. So you have to shade everything other than B. Then you have to take the intersection. Intersection means where you have these both the lines. You will see that these both the lines are there. What is outside here? So that is the case here also. So therefore that is correct. So that is how you understand the De Morgan law, right? So because you can just see yourself, yes, both are the same. Both are the same. Okay, right? So then we have A intersection A. Right. So that is again self-explanatory. If you do A, right, intersection again A, so intersection means you have to have the both the lines. You can see the both the lines are in the area. So therefore we can say A intersection A is A. So similarly, if you take the union also, it is A, right? And what about this A intersection 5? So that is you have A, you are intersecting with nothing. So nothing means you can't show it, you can't show it. So that means you must have this line as well as, if it is A intersection means, if it is A, if it is this is B, you must have both the lines. Now yes, A you have lines, but B is 5, therefore B you don't have line. If B don't have lines, there can't have any intersection lines. There can't be any intersection lines anywhere because B is nothing. Therefore we can say A intersection 5 is 5, because the result is again nothing, because 5 has no lines. Now, nowhere you have the lines for the 5, therefore you can't have a intersection, right? So similarly, A union is E. So that is, so this is your A, right? And this is your E. Union means either this line or that line or both line. Now you can see everywhere either this line or that line or both lines are there. Therefore we can say the result is E. The result is C. Okay. So that is how you get all these things. Right. So now let's look at another one. A union 5. Right. A union 5. So A union 5 means this is my A, right? This is my A. Union 5 means nothing, right? So we remember union means O logic, belong to X or belong to Y. Now belong to A you have some lines, but belong to y, there belong to y or phi, there is no line, therefore nothing is going to added to this one, therefore the result is going to be A, right? So similarly, if it is A intersection E, so this is your E, so let's say this is your A and this is your E, this is your E. Now you can see its intersection, so now the intersection part is only this area, so therefore it has to be A. So likewise, sets you can visualize, right? Sets you can visualize. So the final one is A intersection A complement. So A intersection A complement means A, that is this one, and A intersect complement is this area. Now you can see that there is no area you have both the lines, so therefore it has to be 5, right? So similarly, A union A complement means same diagram, either that line or this line or both you have to take. You can see everywhere some sort of line is there, therefore it is C, right? So those things you don't memorize, so never memorize, just appreciate, just appreciate, then you will perfectly, you are going to understand everything in logic, right? Everything in logic you are going to perfectly understand, you are not going to memorize anything at all, okay? Nothing you are going to memorize. Now we are coming back to the logic, right? So now we are coming back to the Boolean logic. So now we are going to see the connection between sets and logic, right? In Boolean logic, your universal set is going to be true, your empty set is going to be false, the complement operator, the C operator is going to be not, intersection is going to be and, union is going to be O, and XO is just the XO, okay? XO is going to be just the XO. 100% there is a mapping, 100% there is a mapping. That means if you understand sets, you understand logic, right? And if you understand logic, you better understand sets. Actually what you have to do is understand sets and logic together, right? So then it's going to be really easy, right? It's going to be really easy, okay? Right, now let's quickly look at now we are going to do it very fast, right? Because we know that the not operator is just like complement operator, right? Complement operator, if A is true, we say that the complement is false, right? If it is false, the complement is true. Why? Why we say that? Why we say that? So then someone will ask, why you are saying like that? Because in sets, if A is E, right? If A is E, because now remember, E is going to be true, right? E is going to be true. Now if A is true, set, I'm just going to say true means if it is a universal set, its complement is going to be empty set, right? If it is empty set, its complement is going to be universal set. So that we just discuss. So therefore, if E complement is 5 and phi complement is E, in logic we can say A bar, if it is true, this is false. If it is false, this is true, right? In digital logic, rather than true and false, we like to write it as 1 and 0, right? So that means 1 complement is 0, 0 complement is 1, right? And we can, in digital logic, we can represent it using this symbol, right? So let's look at the AND logic now. So AND logic you have to look at like this. So in sets it is intersection, right? It is intersection, that means belong to A and belong to B, right? So in that case we say that if it is belong to both, we say it is AND logic, belong to both. So similarly, if both are true only, the result is going to be true, right? So if both are true only true, if just one is true is not good enough, right? Both has to be true. If none is true, again it's not going to work, right? So now we are trying to understand, if both are true only true, one becoming true is not good enough, right? If both are not true, again it's not good enough, so both must be true. So that is how the AND logic works. So we can understand that using in circuit as well. In electricity is something like you have serial switches. If when both the switches are on only, there is going to have this light is going to on. So that means when both are true only true. If just one becoming true is not going to work, right? So this is how you represent the AND gate. So there, if both are one only one, otherwise it is zero, right? Right. So the next one is OR gate or the OR logic, or in sets we say union. Right. In set we say union. So union means if it belongs to A, or if it belongs to B, or if it belongs to both, we have to take it. But if it is not belong to none of those, then only it is not part of the union. So same thing, when both are false on the false, just like here, if it is belong to both, yes, it is true. If it is belong to A but not belong to B, yes, it is true. If it is belong to B but not belong to A, it is going to be true, right? So in logic we say when both are 0, only 0, otherwise when at least one is 1, it is 1. Okay. So in logic gates or in electricity, it is something like having parallel switches. When at least one switch is on, this light is going to be lighted, right? When both are on, that is also fine. But when both are off only, it is off. When both are off only, it is off. So this is how you represent the O logic in a digital circuit. Okay. Now let's look at the XO. So XO means it must be exclusively belong to A. That means belong to A and not belong to B. Or because A means either this area or that area, it must exclusively belong to B but not belong to A. So that means you can't take that intersection part. So it is just like the O logic where everything was true, but now we have to eliminate this one because it can't belong to both. It can't belong to both. So therefore the truth table is when those both are false, that is this area, and when both are true, it is false, otherwise it is true. That means it must be exclusively belong to A or exclusively belong to B, right? So this is how you represent it in a digital logic circuit, right? So when both are different, right, that is 1 0 is something like this, 0 1 is something like this, it is 1. When both are 1, it is 0, right? When both are 0, that is not belong to A or not belong to B, it is 0, right? So now you can see that I can write it. So that is how your logic start now. I can write it like, right, A and not B, A intersection not B, that is this area, or B and intersection not A, right? So that is why we say A exclusive of B. In logic we can write it like A and B bar, O means plus, B and A bar. So that is how you got this first one of the formula that you have to remember, right? So that you have to have it in your general knowledge, right? A exclusive B is same as A B bar plus B A bar, right? A belong to A but not belong to B, or belong to B but not belong to A, right? So that you have to have that feeling, right? So if you don't have that feeling, after sometimes you are not going to understand complex logic, right? Complex logic, right? So this is not uh, try to make you pass your exam. This is a long journey, right? Finish your BIT, right? So we very few people finish the BIT, right? Only 250 odd people finish the BIT. Why? They can't. After some time, they can't process logic. They can't process logic. Why? They are not seriously looking at these simple things, right? So they try to just pass semester one, but that is not going to work. Okay. So look at those things in a serious manner, right? So A exclusive B, we can write it as A B bar plus A bar B. Why? Belong to A but not belong to B, or belong to B but not belong to A. So that is how that logic works, right? So in real world also you must know that what is exclusive of logic means, right? Without knowing that you can't proceed. Okay, right. Now we have three more logics. Those are just extension to the basic logic, that is NAND, NO and next NO. So NAND means after doing AND, then you do a NOT logic. So that means an AND. So NO means after doing O, you negate it or not it. XNO means after doing XO, you again negate it. So therefore, we get the opposite or the complement of the AND logic as the NAND logic. So because now remember in AND logic, when both are 1 only 1, otherwise 0, therefore in NAND logic When both are 1, 0, otherwise 1. So now you can think similarly and look at the no logic and X no logic, right? X no logic, right? Now we are done with the logic gates. Now this is something you have to remember now, right? So this is something you have to remember. Now this is from sets, right? This is from sets. So you have to remember these things and understand this when you are doing the sets question in your semester 2 paper. This is from logic. So this is your semester 2 logic question. You have to remember and understand these things. And this is what we need for the computer system subject. So this is sets, this is logic, this is digital logic, right? Same thing, same thing. Now you can see those three subjects are not three different subjects. Those three subjects are the same subject. So that is why those people who understand these three together, they feel like exam is not a burden, right? Because all those things are the same concepts coming from different angles, right? Different angles, right. So here we have a complement is again a. Now anytime you can draw it in the Venn diagram and see, verify yourself. Yes, that is a. So in logic we say not of not a is a. In digital logic we say a bar is a. Why? Anyway, these two are the same thing, right? E complement is 5. That means E is true, 5 is false, not true is false, right? 1 bar is 0. 5 complement is C, right? So you know why 5 complement is C. 5 is nothing. Uh, Everything not belong to nothing is our total context. Our total context is only confined to E. Therefore, 5 complement must be E. So similarly, not false is true. 0 bar is 1. Then we know that whether it's A intersection B or B intersection A, it's going to be the same. In that case, in logic also, A and B and A, it doesn't matter, both are the same. So therefore A dot B is same as B dot A. When you are simplifying digital logic, when you see A and B, or when you see B and A, you can just replace it with A and B, right? Why? Just like A intersection B is same as B intersection A. Okay? So similarly, if A intersection B intersection C, you don't care where the bracket is. So therefore here also you don't care where the bracket is. Similarly, for plus or logic also we don't care. When you have the combination of intersection and union, you can just simplify it just like you simplify and multiplication and addition, or multiplication and division. So that is whole for the boolean or the digital logic as well. So a dot b plus c, you can write a dot b plus a dot c. A plus b dot c, you can write a plus b dot a plus c. Why? It's from sets also. You can see that if you shade this area, you are going to get the same area. So therefore, as a logic, this is going to be okay, right? So this is correct. Nothing wrong with that. So see, De Morgan also you can understand like that, right? So why the left hand side and right hand side, we are going to have the same thing, right? We are going to have the same thing. Right, then we have few more, like A intersection A is A. In logic we say A and A is A. In digital logic we say A dot A is A. In sets we have A union A is A. In digital logic we say A O A is A. Sorry, in logic we say A O A is A. In digital logic we say A plus A is A. So whenever you see somewhere A plus A, you can just simplify it and say A, right? A, right? So those things you can now, you are not going to put it as a mechanical. You know that A plus A means A union A, right? We know that A union A is A. So therefore, definitely A plus A is A. So this is difficult for you to understand, right? Difficult for you to remember. But when you see the analogy, you can visualize, yes, A union A is A, right? So we know that A union A is A. So that is perfectly you can understand. But when someone say A plus A, you will wonder what is mean by A plus A, right? A plus A, A plus A. So that is not very intuitive to us, but this is very intuitive to us. That is why we want to see the analogy. And similarly, A dot A bar is 0. Why? A intersection A complement is 5. Right? Same thing, because A complement, A intersection A complement means this is your A and this is your A complement. There is no intersection part, right? So only this line and that line, there is no both line. So therefore it is 5. So in that case, A dot A bar is 0, right? So similarly, A union A complement is E. So therefore, A plus A bar is 1. Right. So similarly, we have all these rules. So you have to remember all these rules, and you must be able to write all these rules so that you can use those things in the exam. So whatever place. Okay. So the thing is, don't just memorize those things. Right. Appreciate those things from sets to the logic to the digital logic. Okay. Right. Then we have few more. Right. Few more. You can use any of these things without any issue. That is A exclusive OB. At any time you can write it as right A B bar plus A bar B. Right. A B bar plus A bar B. So I explained that few times now. Right. So similarly, whenever you see A plus AB, you can simplify it using A. Right. So whenever you see A plus AB or A or A and B, that is A. That is A. Now I know that this is difficult to understand, but look at it in sets. Look at it in the sets, and all of a sudden you are going to understand it. Right. So A, and this is my B, and this is my A, this is my B. So this is A, that is this part. This is union, and this is intersection. So A intersection B means again this one, and it is union of this one and this one, and that union is A. That union is A. So therefore, yes, this is A plus A dot B is A. Right? A plus A dot B is A. Right. So similarly, A plus A bar B. So sometimes you won't see this A bar in my screen. So A plus A bar B means what? So don't memorize. Don't memorize. A plus A bar B means something like this. So this is my A. This is my B. Right. A is this one. Union. A intersection B. A intersection B is this one. Now we have to take a union. Sorry, we have to take the A bar B. Sorry, this is the other way around. So I delete and take it again. So this is A, this is B. Right. So this is A plus A bar B is A plus B, right? So this is my A. Now I need A bar and B. That means belong to B and not belong to A. Now remember, belong to B and not belong to A. What is that area? That is this area. That is this area. Then you have to, they say you take union. So when you take union, what you get is what? A union B. Right? A union B means what? A plus B. So therefore, at any time when you see A plus A bar B, you can say that that is A plus B. Right? That is A plus B. So similarly, if you have something like A plus B dot C plus D, just like in arithmetic, you can simplify say that AC plus AD plus BC plus BD. That means actually A union B intersection C union D is same as A intersection B O A intersection D O B intersection C O B intersection D. Right. So that is again, if you just think as a logic, you will see that this is also logically correct, right? So it's very difficult to draw it because I have draw 4 things, but as a logic, if you visualize it, you will see that this is also going to work, right? So likewise, now we have 23 rules. 23 rules. Those 23 rules you have to not remember, you have to understand, right? So those are the 23 rules, right? In Boolean logic, right? So we gradually came to those rules, okay? Uh, so A bar bar is A, 1 bar is 0, 0 bar is 1, A dot B is same as B dot A plus B is same as B plus A. We don't mind when there are AND operations where the bracket is, O operations where the bracket is. When we have something like this dot and plus together, we can just expand it. This is the De Morgan law, right? Then A dot A plus A is A, right? A dot A bar is 0, right? A dot A bar is 0. A plus A bar is 1. Why? A dot A bar is 0. A intersection not A. That is belong to A and not belong to A is nothing. Right? Nothing is 0. So likewise you have to understand. belong to A or not belong to A means everything, right? Belong to A. So I'm really interested about this. Belong to A or not belong to A. So that means this everything that we are interested. That is E. E means one. Right? E means one. Right? So likewise, A dot 0 is 0. That is belong to A and belong to nothing. So there is nothing has no line. So therefore that is again going to be 0 because there is no intersection lines here because nothing has no line. So likewise a dot 0 is 0. A plus 1, whenever you see a plus 1 you can just simplify and say it is 1. Right? A dot 1 is A. A plus 0 is A. Right? So similarly A exclusive B you can write A B bar plus A bar B. Right? A plus AB you can write it as A. A plus A bar B you can write it as A plus B. And also with just like these three things you can expand four things as well. Okay. So those are the 24 rules. Sorry, 23 rules. So you have to remember those 23 rules. Not you have to remember. Actually you will naturally remember those things. You don't have to put any effort and remember those things. You will naturally going to remember those things. Okay, so that definitely that is going to happen if you understand this from sets to the logic to the computer system, right? So now remember the sets you are learning in your maths, logic you are learning in your maths, this you are learning in your computer system, right? So what three subjects, three topics, same concept. That means once you understand that you have done all three topics, right? Two topics from maths and one of the big topic in your computer system, right? So that is how you understand or organize your stuff, right? Otherwise after sometimes you can't figure it out what is happening. So that is why thousands and thousands people come into the VIT, only 200 odd people finish it, right? So they can't handle that complexity of logic, right? Because they tackle it in different way, they tackle it in wrong way. Okay, right. Now we have concept called universal logic gates. Of course I could have start from the universal logic gate to the Carnot map, but I don't want to do that because the most important part now I have done. Now I am going to do the simple the simple things or the less important part, because the most important part is understanding exactly what is analogic, what is zoologic, what is exologic, what is not logic, right? How those things are related to the sets and stuff, right? So you must have a really good feeling about logic, right? Really good feeling, right? So it's not very dry thing. You must have really live feeling about the logic gates. Okay, right. Now we have concept called universal logic gates. So the NAND gate and NOR gates, those two gates are called universal logic gates. So why we call it universal logic gate is using NAND gate you can create any other gate. That means if you have only NAND gates with you, you can create any logic circuit, right? If you have only NOR gates with you can create any circuit. Why? Using NOR gate, you can create any other gate, right? So that means with only NAND gates or with only NOR gates, you can create any circuits. So therefore, we call those gates as universal logic gates. Okay, universal logic gates. Now let's see. Using NAND gates, how are we going to create other gates? Or using NOR gates, how are we going to create other gates? Okay, right. So this is how you create other gates using only NAND gates, right? Only NAND gates. Now here you can see we can create a NOT gate using only NAND gate. We can create an AND gate using only NAND gate. We can create OR gates using only NAND gates. We can create XOR gates using only NAND gates. So that means if you have only NAND gates, we can create any of the other circuit as well, because circuits have NAND or not XOR and those kind of gates. Okay, so that means using only NAND gate we can create any gates. So let's see why it is going to work, right? Why it is going to work. Now let's look at the now let's see how the NOT gate is created using the NAND gate. Now this is a NAND gate. We know that NAND gate is after AND we do a NOT, right? After AND we do a NOT. So therefore, if you take look at this one, this is A and A. Same thing is now we are feeding to the NAND gate, right? Feed into the NAND gate. That means A dot A, and then we are doing the NOT, right? So we know that A dot A is A, that is one of that 23 rules. A dot A is A, so that means A bar. So that is A bar means, yes, that is what we need when we have A. If you are getting A bar, that is not gate. So therefore, when you need a NAND not gate, you just connect the same input to the two input of the NAND gate, because NAND gate need two inputs, but we have only one input. If you feed the same input, you are going to get the NOT gate, right? So that is the first thing, using not NAND gates, how to create a NOT gate. Now let's see, using NAND gate, how to create a AND gate. Now this is pure logic, you do not memorize. Now we know that if you have a NAND gate, that means AND and NOT. If you again NOT it, it is again going to getting back to the AND gate, right? Because NAND gate is AND and NOT. If you NOT it again, it is going to be an AND gate. So therefore, now we know how to create a NOT gate, right? We know how to create a NOT gate, and this is your pure NAND gate. Now what we are going to do is, after this NAND gate, we are going to have the NOT gate, because this is how you create NOT gate. Because then NAND is AND and NOT. This is another NOT. When you do bar and bar, we know that A bar bar is again A. So that means again we are going to get the AND gate, because this is and NOT, and this is another NOT. So NOT is going to cancel out, and therefore this is going to be your A dot B, right? So don't memorize. Once you understand this, how to create a NAND gate or NOT gate using NAND gate, and then you understand, yes, if you have a NAND gate and if I NOT it again, it's going to be AND. Now you have the AND gate using NAND gates, right? So don't memorize, right? If you try to memorize these things, and when the exam is nearing, you are going to have a lot of pressure, right? Lot of pressure. That is why people fail their exams, right? So you have a capacity. There is a limit you can remember, but there is a big capacity to understand. Okay, big capacity to understand. Right. So the next one is OR gate. Now let's see how to create a OR gate using NAND gates. So if you look at this, right? If you look at this, if you arrange like this, it is going to work, right? For example, now we know that this is a NOT gate. This is a NOT gate. Now let's look at, this is NOT gate means what we get here is A bar, and this is another NOT gate, right? We know that that is a NOT gate. Therefore, what we got is get is B bar, and now what we get here is A bar dot, right? This is B bar. Then this is not AND gate, this is an AND gate. You have to do it again, right? And if you apply the De Morgan law, because we know that A dot B bar is A bar plus B bar, De Morgan law, one of the rules in 23 out of those 23 rules. So therefore, if you take this as a block, that is A bar bar plus B bar bar. We know that A bar bar is A plus B. Yes, that is O logic. That is O gate. So therefore, this is going to work as a O gate, right? So similarly, now you have to remember those things. In the exam, you need those things, right? In the exams, they will give you a question and say, using only NAND gates, how many NAND gates will be needed to create this particular gate, particular circuit. So then you must know, if you have O gate, this is how you are going to create a O gate using NAND gate, right? O gate using NAND gate. Right, now if you look at the final one also, it's a little bit complicated, but at least you have to remember how many NAND gates are needed to create XOR gate, right? So here you can see you need four NAND gates. If you want to, you can just simplify this, take it as exercise. It's a very good exercise, right? So don't take anything for granted, right? So now this is the expression for this particular thing, right? Because you can see A dot B bar is there. Then for that again A is input, and again you are taking bar and blah. So if you simplify this, what you are going to get is A B bar plus A bar B. So do it as exercise, right? You will get something like this, and we found that, and one of our 23 rules is, this is A exclusive of B, right? So remember, so we had this as one of the rules, right? And one of the rules, right? So remember, A exclusive of B is A B bar plus A bar B, right? So therefore we can say that, yes. So you have to simplify this and get this, right? Once you got to this point, you can say that is A exclusive of B. Why? Why we know that A exclusive of B is in sets. in sets A exclusive of B means exclusively belong to A or exclusively belong to B. Belong to A but not belong to B, right? Belong to A but not belong to B, or belong to B but not belong to A. So that is this part, exclusive this part. Now you can see you are not just machine, you are not a machine, you are an intelligent person. Right, so act like an intelligent person. Don't act like a machine and try to memorize things. Right, so that is not going to work. So what we need is humans, intelligent people. Machines, we have so many computers, right? So you don't want to be a computer, right? So yeah, you can't be a computer as good as the modern computers, but you can be a as good human as anyone else, right? So that is why intelligent, right? So don't try to memorize things, okay? Right, so that is using NAND gates. You can create any gates, right? Using NAND gates you can create any gates. Similarly, using no gates also you can create any gates. So at least you have to remember how many gates are needed to create a particular gate using no gates as well, okay? So because you get that kind of questions, again it's a very good thing. You simplify those things and see yourself, yes, this is going to be AND gate, this is going to be OR gate, and this is going to be XOR gate. Okay, so that is something you have to do. Right. So I explained this one. So similarly, you try to understand or appreciate why these things are going to work. Now you can see these NAND gates and NOR gates are really funny gates. Using only those gates, we can create anything, right? Any circuit. Right. Now we are moving to the designing of the digital logic circuits, right? So if you have any questions up to this point, you have to raise those questions, right? But ultimately, if you don't have any questions, you can get 100 out of 100 from the exams, right? Either you have questions or you get 100 out of 100. So you can't have any other things, right? Either you have questions or doubts, or you get 100 out of 100 from the exam, right? So you can't say I don't have any doubt but I can't get 100. So that is logically that can't happen. So that means if you can't get 100 out of 100, you are not confident enough. Still you have doubts, right? Still you have doubts. So if you have doubts, that is why I keep on asking, raise those questions, right? Still I don't understand this particular thing, right? Don't be shy, right? So it's you must be ashamed, not by asking questions, not by not understanding, and still you don't know whether you understood or not, right? Now we are going to discuss is how to design a circuit, right? How to design a circuit. Uh, so there are two approaches we can use. Either we can go for a sum of product approach, or we can go for product of sum approach, right? So we can go for either sum of product approach, or we can go for the product of sum approach, right? So sum of product means sum means O, product means AND. So therefore basically when we say sum of product, it is O of ANDs, right? When we say product of sum, product means AND, sum means O, that means AND of O's, right? So either we can create O of ANDs or AND of O's. So sum of product means we have some elements like A, right? So we have elements like A, B bar, right, plus A, B plus A bar, B bar. Now we can see everywhere those are products, and now we are summing it. So that is called sum of product. Product of sum means first we have some sums like A plus A, B plus C, then A plus B bar plus C bar, etc. Then we are taking the product. So that is why I said product of sum. Say A bar plus B bar plus C. So likewise here we have the sums. Now ultimately we are doing the product. So that is why we call it product of sums. So these are called sum of products, and these kind of statements are called product of sum, right? So everywhere you need to have all these variables, right? A B everywhere, either its own value or complement value, right? Own value or complement value. Likewise, that if you there can be a situation where in some place maybe C is missing, so that is fine. That is fine, but you need to have all the here you can't have another anything else like XO or whatever. It must be all sums here and product. Or here all products here and here sum. Okay, right. So then so that is format, right? Sum of product format, product of sum format. Now let's see, given the input output combination, how to create a sum of product circuit. It's very easy. It's very easy, right? So this is a usage, or maybe someone has this requirement, right? This is just a requirement. I have given you a random requirement. Say assume that there are three inputs and we need output. So how my output is going to work, or what is my requirement is this. So when both are all are zero, I need 1 year. That means when all are zero, I want to have 1 year, right? That means all are having no current, we need I need current here. When these two are zero and this one is one, I want zero here. So likewise, I have given you the requirement. I have given you the requirement. So now I am asking you to come up with a circuit for that, right? Come up with a circuit for that. So in sum of product approach, what we are supposed to do is mark only the outputs having one. Mark only the outputs having one, right? So in this case we have these three only. Then write it as product, because this is sum of product. So how we are going to write the product? If it is zero, bar it. If it is 1, write it as it is. Now this one says what? A bar, B, C bar. Right? This one A, B bar, C. Right? So then you have the product. Finally, for product is only for those having 1. Finally, you sum it. You sum it. So that is how you are going to get that. So if you have this particular expression, that is going to work. That is going to work. So now what you have to do is, as a machine, don't think that this is going to work. As a logic, can you explain to someone why this is going to work, right? If you can explain to someone, yes, this is going to work, then you are done, right? So no point as a machine by just marking these things and writing this expression. Yes, that is not going to work. If you can explain to someone else, maybe your friend, why this is working, or why this expression is going to give these input output combinations, that is what is needed. That is what is needed. Okay, so I am not going to do that. I am just keeping it as a exercise for you, right? Exercise for you. Can you explain it, or maybe you can just put it in the WhatsApp group, right? If you like, can you explain why this is going to work, right? Why this is going to work, right? So that is very important, right? Don't do it just like a, don't do just like just memorize it. Okay, right? So now the next approach is the product of sum. So similarly, if you are given different ones, different places, now you should be able to write it and sum it. But the most important thing is, can you say, or can you explain why it is happening, why it is happening, right? So I just want to give at least one person, if you like to talk, can someone explain why this is going to work? Let's see whether at least one person has the guts in this session. Can someone tell me why this is going to work? Anyone here want to give a try? So that is confidence, right? So that is leadership. So no one is having that guts. Anyone having the guts to explain this? No one. So that means you have to think about it. Right? You have to think about it. Right? So I just keep it as open thing. Right? I'm not going to explain it to you. Right? So if you can explain it, you are done, right? You are done. You know exactly how the AND logic operate, how the OR logic operates, right? How these things are happening, right? So I know that anyone will be able to write this, will be able to write this expression, but very few people can explain why this expression can work, is going to work, right? So why it is going to work. So that is your task, not learning how to write this expression, and understanding and ability to get the ability to explain why this is going to work, right? So that is the important thing, right? Right. So no, anyone want to give a try? No. So that means So you don't have the confidence. You don't have the confidence, right? Right. So next one, product of sum. In product of sum approach, what we do is again we will be given an input output combination, right? We will be given input output combination. If they ask you to come up with a product of some type of a circuit, what we have to do is we have to mark only output having zero, right? Output having zero, then write it as a sum. But when you are writing it as a sum, make sure that now zeros are taken as it is. Now earlier remember ones were taken as it is. Now zeros are taken as it is and ones are taken as complements. Now in this case it will be a bar plus b bar plus c. This one will be a bar plus b bar plus c bar, right? So likewise you write the expressions related to those zero values. Those are the sums. Now you multiply it or now you product it. So product means n, right? So plus means o. Then it's going to work. If you take any combination, random combination like 0 1 1, and assign it to this statement 0 1 1 and simplify, definitely you are going to get 0 because output is going to be 0. If you take something like this combination and simplify this expression, you are going to get 1. So that means for each and every combination, definitely whatever the output here you are going to get, right? But the thing is, can you explain it to someone? So that is why logic is all about, right? Can you explain it to someone? Yes, it is going to happen because of this particular way. This is how the logic works, boolean logic works. Therefore definitely it is going to this is going to work. So that is what we need. That is what we need, not machines who can convert this to this kind of a thing. So we don't need humans to do this, right? Even the computer can do this, right? Computer can do this, but we need humans who can talk and who can explain why this is going to work, why this going to give all these possible for all these input combination, why this is going to give the correct output combination, right? So I keep it as open thing, right? So try to explain it to maybe your friend and see whether he can understand it, right? Or just put it into the WhatsApp group so that we can see whether you have properly understood it, right? If you are shy to talk, right, right. Now we know that when we are given the input output combination, we can come up with either sum of product circuit or product of some circuit, right? Either sum of product circuit, product of some for even for the same thing, right? Now we have two options, right? So this circuit is also going to work if it is the same truth table. The other one is also going to work, right? So it's going to work perfectly, going to work. But now what we like to have is not the circuit, come up with the simplest possible circuit, right? If there's a simple circuit, so the simplest circuit if we can find out, that is benefited. Why? It's going to be less costly because you need less number of gates, and also your circuit is going to be smaller. When you have lesser number of devices still doing the same thing, then it is going to be less costly and smaller in size. So we like both. So now how to do that, or how to find, once you get this expression, or once you get this expression, how to find the simplest possible one. Maybe this is not the simplest possible one, but this is going to work. But there can be a place expression which is simpler than this. Again, it's a sum of product, but it is simpler than this. If so, how to find that? So there are two approaches. First approach is, you use the Boolean algebraic rules. So remember we explained 23 rules, right? 23 rules. You apply those 23 rules in a smart way and come up with the simplest possible one, right? So that is somewhat difficult task. I am not saying it is impossible task, but it's a somewhat difficult task, right? So there's another approach, we call it use of Carnot map. Use of Carnot map. So when you are using Carnot map, it is relatively easy. When I say relatively easy, it is easier than this approach. Easier than this approach, right? So I am not saying this is very difficult task. Of course, you can do this. right? But we have a easier approach. So why don't we learn both the approach then, right? So we learn this approach as well as this approach. But when it comes to real world scenarios, you will always use this approach because you know that it is easier. But for your understanding and stuff like that, we better understand that approach as well. But yes, if someone is using this approach, another one is using this approach, this guy is going to get the results bit faster than this guy. Even you yourself, once you try this approach, once you try this approach, this from this approach you are going to get the answer faster, right? Much more faster. So, but therefore, let's first try to understand the second approach, which is the easy approach, right? So we call it use of Carnot map. Use of Carnot map. Okay, right. So what this Carnot map does is, right. So I first explain what does this Carnot map is doing. So maybe you have already done this, right? Maybe you have already done this. Maybe so some of you guys have come to our class. Maybe some other class. Some of you, I know that some of you guys are doing self studies, right? So all are okay. Can someone explain? Right? Can someone explain what is the idea behind Carnot map? Because this is revision class, right? This is not I'm first time teaching. I'm first time teaching to set of students, so you are first time learning this stuff, right? This is a revision. Now the exam is very close by. Can someone explain me what is the idea behind Carnot map, or why we draw a Carnot map? So people who can answer that kind of questions are going to get the degree, not the mechanical people. Because year one you can be a mechanical person and somehow pass your year one, but especially in your final year, don't just tell me it is to simplify, right? Uh, you have to explain. But remember, we are writing once, we are drawing some regions, right? Then we come up with some things. So why we are doing that? Why we are doing that? Why we are doing that? Can someone tell me? Because this is not the first time you are going to see the Kano map, definitely. So Kano map is something like this. You know what is a Kano map is, right? So Kano map is something like this, right? You draw regions, you come up with expressions. So why you are doing these things? That is my question. Why you are marking regions like this, then writing individual things? What is the idea behind this? Because there is logic behind that, right? So the person called Kano came up with this concept. The person called Kano came up with this concept. Anyone? Still I didn't get a reasonable answer? Right. So I will explain. So that is the most important thing, right? So right. So I will try to explain why we want to draw Kano map, right? So it's something like this, right? Something like this. Uh, Now let's take some example. Okay. Now let's take an example. Right. Close look at what I'm going to do. Right. Assume that I have these uh, three inputs A, B, and C. Okay, A, B, and C. So now you know that if we have three inputs, there are altogether just give me 1 second. Right? A, B, and C. Now look at what I'm going to do. So these are the possibilities: 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0. How many we have? 1, 2, 3, 4, 5, 6, 7. The final one is 1, 1, 1. Now this is my input, right? This is my input, and this is my output. Output. Say this is my 1, this is 1, this is 0, this is 1, this is 0, this is 1, this is 1, and maybe this is also 0, right? And if you write the, say sum of product, so this is now we have to take the ones. This is going to be A bar, B bar, C bar, and this is going to be A bar, B, C bar, and this is going to be A bar, sorry, right, A, uh, A bar, B, C, right, A bar, B, C, and this one is going to be A, B bar, C, and this one is going to be A, B, C bar. Right, now you get the expression. What is the expression? A bar, B bar, C bar plus A bar, B, C bar plus A bar, B, C plus A, B bar, C plus A, B, C bar. Now this is going to work, but this may not be the simplest possible thing. Simplest possible thing. Now, if I ask you to simplify this using those rules, different people will come up with different solutions. So I will give this as a exercise. Can someone okay? So for bar you can just write a dash or whatever. Can someone tell me what is the result of this one? Or what is the simplest possible one for this one without using Carnot map? Simplify it and give me the answer. So just take it as a challenge, right? So you can just write it as a dash b dash c dash plus a dash b c dash plus a dash b c plus a b dash c plus a b c dash, right? Just give me the final answer. I am pretty sure that if I get 3 answers, maybe if I get 10 answers, 10 people giving me the answers, I will have at least 4 or 5 answers. 4 or 5 answers. So I will also try to do this because this is for me also this is a hard problem, right? This is more difficult than using Hanover, right? So one thing you can do is you try to figure it out. Okay, which one you are going to factorize, right? So for example, here I can see A bar and C bar is common, right? So you can see A bar and C bar is common. Therefore, I will try to take A bar, C bar. Then it will be B bar plus B, right? So there can we have any other things like that? Here A B, right? So nothing like that, right? So here can you see any common things? C is common, but nothing other than C is common here, right? Only C is common, right? So then it is A bar B plus A B bar, right? If you take these two, only A is common. If you take these two, only B is common. So it's not going to be. It's going to be a tough task. It's going to be a tough task to find the simplest one. Of course, this I can say B plus B bar is 1. Then this one will be A bar, C bar. But other things, it's very difficult to simplify. So can someone give me the answer? So I know that it's going to be difficult task, right? Right? Right. So now let's see what will happen if you draw a Carnot map. Now I will again, now you got a chance to see the difficulty, right? See the difficulty. Now can you explain what is the idea behind Carnot map? Right. Now let's see. Now let's draw a Carnot map and see why Carnot map is going to make it more simpler than this one. Because if this is simple, no one is going to draw a Carnot map, right? Because if this is very simple task, why we want to put it into another sort of map situation, mark the regions, right? So many things, right? If this is easier than the map one, no one is going to go for the Carnot map, right? Definitely Carnot map is easier. That is why we go for Carnot map, right? The thing is, you have not experienced that this is difficult. This is difficult. Yes, this is really difficult actually, right? So now I am stuck here. I am stuck here. I don't know from here what to do, right? Now I have to do some guessing and try few things. And again, I don't know whether I got the simplest one or not, right? I might get a simpler one, but still it may not be the simplest possible. So then again, I am in doubt, right? So the best thing is take some time and come up with the answer for you yourself and again draw the Carnot map and you will see most of the time 90% of the time you will see that okay my answer is not the simplest one. So the Carnot map I got the even more simpler one, right? So that is why we go for Carnot map. Still I didn't explain you why Carnot map is going to solve the problem, right? So that is the question I asked from you. Why Carnot map is going to solve the problem, right? So can someone tell me why or what is the idea behind Carnot map? Right. So we'll come back to this one. We'll come back to this one once we understand how the Carnot map is going to work or how we are going to solve the problem using Carnot map. Then we will come back and see why Carnot map is going to work. We'll keep this as it is, right? Right. We'll keep this as it is. Now let's move on to Carnot map first. Right. Now let's see the theory part or the idea behind Carnot map. Okay. So my question is still open. Anyone can answer it. Alright. You can answer it. Right. Use of Carnot map is a graphical approach, right? It's a graphical approach. First, we transform our input-output values to a map, right? So what we have is a table, okay? So what we have is a table, right? We are going to transform this input-output table into a 2D map. This is a 2D table, right? We are going to transform it to a 2D map, right? Transform the input output values to the Carnot map. Then we are going to mark the regions, right? We are going to mark the regions. The third stuff is once you mark the regions, we are going to derive the SOP or the POS expression, right? So transform it to the Carnot map, mark the regions, come up with the expression, right? So those are the three steps we are going to do, right? So you have something like this rather than go for this approach because this approach may not give you the simplest possible one and it's going to give you a lot of headache to find out which is your simplest one. You might do some sort of a simplification but you never know whether it's the simplest one, right? That is the issue. That is the issue, right? So that is why I'm asking you to do it as an exercise. You spend some time and come up with the expression, then again draw the Carnot map and all of a sudden you will find that okay my one is not the simplest one, right? So Carnot map gave me even simpler one. So that is why we go for Carnot maps, okay? Right. So these are the three steps we do. Transform it to the Carnot map, mark the regions, derive the expression. right? That is not a difficult thing. That is not a difficult thing. Now let's see how to transform it to the Carnot map first. So when it comes to Carnot map, we are going to transform that tabular thing, right? This tabular thing, so you can see ABCI in one side, right? ABCI in one side. Now maybe AB is in one side, C is going to be another side. So that is why we say it's moving to a map now. Now you can see B is here, A is here. Earlier both A and B it was in this were columns, but now one is column, the other one is row, right? So if it is two variable, that is how you do it, right? One become the column, the other one become the row. It can be anyone, right? Maybe A is here, B is here. If you have three variables, you have to go for 2 and 1, right? Again it can be 1 or 2, 1 2 or 2 1, right? It can be anything again. It can be A B and C, or it can be A and B C, or it can be A and BC, or it can be AC and B, it doesn't matter, right? What you have to do is make it 2 1 combination, right? 2 1 combination, right? Either here 2 and here 1, or here 1 and here 2, and again anything. It can be even here B, here AC, or here AC, here B, or here AB, here C. Anything. Only requisite is divide it into rows and columns, right? Divide it into rows and columns and try to make it as much as possible even. But when you have odd number, you can't make it perfect, right? Then go to at least nearly equal to two equal parts, nearly. Again, if it is four variables, you can perfectly subdivide it to 2 and 2. 2 and 2. Whatever the way you want, maybe A, B and C, D here, or A, C and B, D here, or C, D here and A, B, whatever the way you divide it. Again, if it is 5, again you can't go for perfect division, it has to be 2 and 3 or 3 and 2. Okay? Right. So, transform the input output values to a 2D map. 2D map. So, that is what we have done here. Then, when you are doing this numbering, you have a rule here: no two consecutive columns or no two consecutive rows can have more than one input value chain. So that is a rule. That is a rule the Kano came up with. So that means now here there is no issue here, because from 0 here we are moving to the 1. From here 0 you are moving to the 1. When you are moving from here to here, only one value has changed, that is 0 has become 1. So when you are moving from 0 to here to here, only one value has changed, that is 0 become 1. But when you have two variables, you have to be very careful. Now here you have to ultimately you must have all the combinations, right? Because C we can just have 0 and 1 here, but here now you have two variables A and B. So therefore now we have four combinations: 0 0, 0 1, 1 0, 1 1, right? Again, when you are writing, you can't break this rule. No two consecutive columns or rows can have more than one input value change. Now when this is 0, when this is 0 0, my next one can't be 1 1. Why? Then this 0 has become 1, this 0 has become 1, that means two variables have changed, right? So this says no two consecutive columns or rows can have more than one input value change, right? You can have only one input value change, not more than one. Here more than one input value change. So that is why we write like this: if it is 0 0, next one must be either from 0 0, so the next one must be either 0 1, or it can be 1 0. Both are okay, because in this case this one is not changed, only this one has changed. If it is 0 to 0 0 to 1 0, this one is not changed, only this one is changed. But if it is 0 0 to 1 1, this one has also changed, this one has also changed. So you can't break that rule, right? So that is why after 0 0 you have 0 1, or it can be 1 0. Then after 0 1 you can't have 1 0, because if it is after 0 1 1 0, you are again breaking the rule. 0 has become 1, 1 has become 0, right? So you can't break that rule. You have to have your data without breaking that rule. But again, you might even start with 1 0 here, or you can even start with 1 1. As long as you don't break this rule, that is fine. That is fine. Okay, so that is how you prepare the Carnot map. Then you have to transfer your input values and output values to here, because this is your input value. And now depending on the output values, you will fill it like whatever the one values, you will fill like this, right? Then remaining things will be zeros like this, right? Say zeros like this. So that is your type first thing. put it into the Carnot map. Now we had a problem here. Now let's do that now. Okay. Now we have this sort of a thing. Now let's prepare the Carnot map for this one. Okay. Now this is a three variable thing. Three variable thing. Therefore, we have to go for one and two, or two and one. Right. So either we have to go for 2 1 possibility or 1 2 possibility. So I will go for, right. I will go for something like this. So let's say this is my AB and this is my C. Or you can say this is my A, this is my BC. It doesn't matter, right? So this is my 0, 1. Again, it can be 1 and 0. It doesn't matter. There is no rule saying you have to start with 0, right? Again, there is no rule saying you have to start with 0, 0. But usually we start with 0, 0 as a convention, okay? So that everyone has sort of same thing. 0, 0. Then I can go for either 0, 1 or 1, 1, 0. I will go for 0, 1. Then I can't go for 1, 0. I have to go for 1, 1. And then 1, 0. Now I have not break that rule, right? Right, now you can see 0 0 0 is 1. So 0 0 0 means AB is 0 0, C is 0, that is 1. Then 0 1 0, 0 1 0 is this one 1. Then 0 1 1 is 1. So 0 1 1 is 0 1 and this one is 1, that is 1. And then we have 1 0 1 is 1. So that is 1 0 and here 1, that is this one. And then we have 1 1 0 is 1, that is this one is 1. Then we know that others are zeros. We have three zeros, this one, this one, and this one. So that is the first step we are done. Transform it to the Carnot map. Transform your tabular data into the, now here all are in the columns, now here columns and rows, columns and rows. Inputs are in columns and rows, outputs are also here now. Okay. Now we are done with the first step. Now we are done with this first step. Now let's move on. Right. So second thing is, now you have to mark the regions. Right. Mark the regions. So marking the regions means ultimately you will be doing something like that. Okay. So when you mark regions, these are some rules. So don't think that those are very complicated things. Those are very simple things, right? Uh, if you are really interested about this subject, naturally you are going to remember all those things, right? Right. So the first thing is, it's a map, right? So the first rule says it is a map. So that is why we call it Carnot map. So when we say map, right? When we say map, what you have to remember, what is coming to your mind first is the world map. Right? World map. Right? So if you take the world map, we know that we have America here, right? Then South America, then the Europe, Africa, India, right, etc. And we know that when we go somewhere little bit beyond this, you ended up with Japan, right? So that is when you go little bit beyond Australia, you ended up with South America. So that is this thing and this thing is close by because it's just sphere. You just break it and draw it, right? So this one and this one is close by. But in world atlas or world map, this one and this one is not nearby because this is north hemisphere or the north pole, this is south pole, right? So we can't say when we move little bit from here, you are coming from here. No. So that means yes, these two line areas are nearby, but these areas are not nearby. But when it comes to Carnot map, it's a perfect map. It's a perfect map. So that means when you draw a Carnot map, you can think that this one and the bottommost are the nearby. Not only that, your leftmost and rightmost are nearby. So it's sort of a perfect map, which is not the case when it comes to a world map. Only these are nearby, but these are not nearby. But in a Carnot map, you have to consider that the topmost and the bottommost are just like sit next together. The leftmost and rightmost are sitting next together. So that is a perfect map. It's a map in both the dimension, which is not the case in this kind of map. Okay, so that is your rule number one. That is your rule number one. Consider it as a sort of a perfect map in both directions, right? That is your rule number one. Second rule says you have to start grouping ones, right? Grouping ones, but that region must be either square or rectangle. Square or rectangle. And the size must be 2 to the power n. Right? That means either 1, 2, 4, 8, 16, etc. So that is your rule number 2. Right? Rule number 2. The rule number 3 says always mark the current largest possible region like you are having. So first you have to look at what is the biggest region right now, mark it. Then go for the next biggest, next biggest. When you have a size of 4, you can't mark size of 2 region because the currently the biggest region is 4, right? So that is another rule. So you have to first find out what is the current biggest region, then go to the next one, then go to the next one. If there are two current same size thing, of course you can go for any of these things when it's a type. But when you have two size of things, you always have to mark the bigger guy first. Okay, right? So the always mark the current largest possible region and so on. Then the next rule says overlapping is allowed and preferred. So that means when you mark a region like this, right, covering one, you can have overlapping like this. That means the new region also have the part of the old region. So that is allowed and also it is preferred. So whenever there is a possibility, overlap. But only thing is your new region must have at least one unused one, right? So that means overlapping is allowed, but your new region must have at least one unused ones as well. So that means something like this. Say this is a region and this is another region, this is another region. And then you can't say this is a region because here no unused one. These ones were used earlier, these ones were used earlier, right? So you can't do like that. So you must have at least one unused one. So if you have a few more ones here, then you could have drawn like this. Okay, right? So the new region must have at least one unused one, right? Then when all the ones are consumed, you are done. So when all the ones are consumed, you have to stop, right? So that's it. That's it. So that is how you mark the regions in Carnot map. You have to consider it as a map. That means the leftmost and rightmost are nearby, topmost and bottommost are nearby. Try to mark only, not try to mark only squares and rectangles only, covering only ones. You can't have zeros in your regions, right? Make sure first you draw the mark the biggest possible, next biggest possible likewise, and also always try to have overlapping. So because when you have overlapping, you will get bigger regions, and your new region must have at least one unused one. Finally, when all the ones are done, you are done. Okay, you are done. Okay, now let's get into our example where we have been trying to do. Right, now let's see. Without violating those rules, I am going to mark the regions. Now let's see. Remember the sizes are possible sizes are 1, 2, 4, 8, etc. Now I can't see any 8 size region, right? I can't see even any 4 size of 4 regions also because this is 3, this is 3, right? So this is 1, right? So I can't even see size of 4 as well, right? Size of 4 as well, because this is just 3, right? This is just 3. I can't mark something like this T shape, that is not a square or rectangle, right? So then I have what I have to see, there is no 4 size of 4 regions are also not there. Then I have to look for size of 2 regions, size of 2 regions. Of course there are size of 2 regions, right? So you can see this one is a size of 2 region, right? Then again you have to look for size of 2 region before looking at the size of 1 region. Now you can see that okay, this if you combine these two together, that is also size of 2 region, right? Size of 2 region, because I don't have a size of 4 regions, right? Now rather than taking this alone, right? Rather than taking this alone, if I combine with this one, that is another size of 2 region because if size of 2 regions are only, I have to look at the size of 1 region, right? If size of 4 regions are only, you have to look at the size of 2 region. Obviously there are no size of 4 regions here, and now this guy I can't combine with anyone else, right? So because this guy is alone, if there's a 1 here, I could have combined these two because these two are consecutive, but nothing is there, therefore this guy is alone, right? Now the regions are done. Now the regions are done. Without violating those things, I draw the regions. Okay, right. Now let's move on to the third thing. Now we have done two things. Put it into the Kano map, mark in the regions. Now let's move on to the third one. Right, so this is how we mark regions, right? Different places. We'll do few examples when we are doing the exam papers. Right. So derive the simplest possible SOP. Now we are done. Now we are in the final stage. Once you mark the regions, using those regions or those areas, we are going to come up with the simplest possible expression. Okay. So this is how you do this. Write down the input value. So there are different approaches. This is little bit lengthy approach, but very mechanical approach where you don't make any mistakes, right? So if you know any other way, just use whatever the way you want as long as you don't make any mistakes, right? This is just one approach I am going to explain. Write down the input values of each cell in the regions, right? Identify which columns have the same value repeated, right? So when you write it, identify which column has the same value repeated. Either it can be 1 is repeating or 0 is repeating. Write the product for each region, right? If 1 is repeated, take the input variable as it is. If 0 is repeated, take the complement of the input variable, sum the product of each region. So that's it. Okay, so you will understand this. Of course, you may have already know this thing, but let's do this for our one, right? Right. So now what we are going to do is take one. This is my approach or our approach. So let's take this. Now we have three regions: this region, and this region. Okay. Uh, so let's take this particular region. Right? So that is I am going to write A B C. This guy is 0 0 0. Can you? I hope you can see my cursor movement. If you can't see the cursor movement, just put up a message to the WhatsApp group. Then this one is 0 1 1. Sorry, 0 1 0. 0 1 0. So you can see this guy is not changing, this guy is not changing, and these guys are zeros. Therefore, this is A bar, C bar, right? So I can't take this one because in column wise it is changing, right? But this is zeros that is changing, not changing. Therefore, those are bars. I'm done with that. Now let's take this one. A B C. This is 0 1 0. 0 1 0, and this guy is 0 1 1. 0 1 and 1. 0 1 1. And now you can see this guy is not changing, this guy is not changing. This guy is a 0, A bar and B. And now let's take this region. A, B and C. So this is 0 1 0, and this is 1 1 0. 1 1 0. So this guy is not changing, this guy is not changing, this guy is a 1, this guy is a 0, that is B C bar. And of course this guy I just have the A B C as 1 0 1. 1 0 1. Right, now I am done. And now write those things as, so 1 0 1 is actually now because we have only one, we can say always they are not changing. So therefore this is A B bar C. Right, now I am done with those things. Now what I have to do is I have to write it as a sum. Write it as a sum. Then I am done. So my final expression is say A bar C bar plus A bar B. So I have to take the expression for each and every region. There you have the B C bar plus A B bar C. So that is the simplest expression. That is the simplest expression, right? So remember we had a big expression previously. We had a big expression like this. It has been simplified. It has been simplified to this one. But if you try to use your rules, you will take little bit of time and lot of guessing and come to here. And again, when you come to here, also you are not very sure whether it's going to be further simplified, right? So that is uncertainty is with you. But when it comes Carnot map, you know definitely this is the simplest sum of product approach, right? So definitely there's nothing simpler than this one. Okay, so that is the beauty of Carnot map. That is the beauty of Carnot map. Now let's see why this Carnot map is going to work. So that was my original question, right? So these things anyone can learn, right, by reading or looking at a video. But if you are an intelligent person, by looking at these things in a very systematic way, You have to understand why this Carnot map is going to work. Why this Carnot map is always giving me the simplest one. Right? Why this Carnot map is giving me the simplest one. Now I am giving you another opportunity after seeing this. Now can someone explain why when you do this systematic thing and marking the region and blah blah blah, why we get the simplest one? Why we get the simplest one? Can someone explain? So I have got some answers, but they never explain why. They just say came and provide an alternative way. So what I'm asking is why this alternative way is working, right? So another answer is we can simply or easily simplify things. So what my question is why this is going to work, right? Why it is going to work? So the most important or the most beautiful word in language is why, right? So a lot of people don't care why, what they are interested is what or how, right? So they are really interested about how, they don't care why, right? So but intelligent people, they care about why, they care about why, they don't just accept things for the granted, right? So they think about why, right? So the Kano came up with this idea, right? So you can see Kano is a smart person, right? So he found this, right? So he found this. At least we have to understand what is his thinking is, right? So we are not going to find it. He only found the issue way. We at least as a human, this is something a fellow human has found. At least we have to appreciate his finding and also try to understand what is the thinking behind it. Right. So this is the idea behind that. So because otherwise we will be losing some time. So the idea is something like this. Okay. Now when you are doing mathematics, you have done this kind of thing. Right. So when you are asked to solve something like x squared plus 5x plus 6. Now you are supposed to factorize this. So you are supposed to solve this. Now you know how to solve this. Now usually we want to factorize this, right? But you don't see the factors here, right? If you can do the factors like very easily, we can say okay, something like this is 0, then either this must be 0 or this must be 0, because this is 0, this is x value is this one, because this also can be 0, x value is this one, and you are done. But when you have this kind of a scenario, you don't know what is it. But mathematicians didn't say just keep it open and say that okay, we don't know what is this and let's forget about this. So they came up with a technique, right? So mathematicians came up with a technique to factorize this and solve this. So what is that technique? So their technique, you know, can put it into two parts, right? Put it into two parts. Don't just break it to two parts like 4 plus. Now you can say something. Someone will say, okay, let's put it as 4 and 1, or let's put it as minus 7 and minus say plus 7 and minus 2. So rather than just arbitrarily doing this, right? So because there are so many possibilities, right? So so many possibilities. It is just like it's just like by looking at this, and I am trying to figure out am I going to combine these two? Am I going to combine these two? Am I going to combine these two? I have no idea which one I want to combine. So mathematicians came up with a smart idea, that is they told us don't just randomly try out things. Right? Don't just randomly try out things like 4 plus 1 or minus 7 minus 2 or 10 minus 5 or whatever. We will give you a proper solution. So what is that solution? Break it to 2 such that when you simplify you get this one, when you multiply you get this one, then definitely it is going to factorize. So that is what the mathematicians found, right? So that means when you multiply you must get 6, when you simplify you must get 5. We know that that is 3 and 2, because 3 into 2 is 6, 3 plus 2 is 5. So therefore we can very easily say, we can just put it 3x plus 2x plus 6 equals 0. So now I know definitely this is going to be factorized. Definitely x we can take it out, x plus 3, and let's take it out 2, x plus 3 which is 0. Now you can see all of a sudden the factors are there. Factors are there. But if you just put it as 4 and 1 or 10 and minus 5, it is not going, it's never going to happen. Right? So now we know that x plus 3 into x plus 2 is 0. Now I know that either this one must be 0 or this one must be 0. Therefore, x is minus 3 or x is minus 2. So I got the answers. Right? I got the answers. So mathematicians came up with a definite technique or tactic. So the Kano came up with the same sort of a solution. So that is exactly the same sort of a thing the Kano did also, right? So rather than try randomly figuring out what which one we are going to combine and apply which rules, he came up with something like when you multiply you must get this one, and when you sum it you must get this one, similar thing. But this problem is even difficult, so therefore he had to do all these things that we did with Carnot map. Right, now let's see. If I have the Carnot map, I know how to get the answer now, right? So actually Carnot, now we are going to reverse engineering or the understand what the Carnot's idea is, what the Carnot try to figure it out, right? Now you can see that this value is in this region, it is in this region, and it is in this region. Now you can see this particular value, this particular one is in three regions. So what is this particular value? That is 0, 1, 0. That is 0, 1, 0 means A bar, B, C bar. Right? A bar, B, C bar. A bar, B, C bar is in this region, that region, and the other region. So what is that? A bar, B, C bar. Now I am going to do that. Right? So which is what I am going to do is I am going to write like this. So where is A bar, B, C bar? A bar, B, C bar. Right. So this one. This is that one. So I am going to write it as, I am going to write it three times now, right? Three times. So that is, uh, so I try to write it somewhere here. A bar, B bar, C bar plus A bar, B, C. That I took this one, plus A, B bar, C plus A, B, C bar, right? So then A bar B C bar I am going to write three times. Right? A bar B C bar I am going to write three times. So I am just going to delete this. Right. So I am going to write uh, A bar B C bar three times because I know that it is in three places. Right. A bar B C bar, again A bar B C bar, and again A bar B C bar. I can do that without any issue because we know that A plus A is A, right? So therefore I can, when I have A, I can say A plus A, and even we know that if it is the case A plus A plus A is also A, because A plus A is A, then A plus A is A. So therefore I am not changing the expression, the big expression, I am just writing it yeah, rather than once I am writing it three times. Then I know exactly what to factorize because I know this region means, right, this A bar B C bar and A bar B bar C bar. So that is this guy and A bar B bar C bar. So I can factorize these two. So that is why we have this region, right? So then this region means A bar B C bar and A bar B C. So that is this guy and A bar, right? So this guy, this region, A bar BC. A bar BC is this guy. So this one and this one. So then this region, that is A bar BC bar with A B C bar. A B C bar. That is this guy. ABC bar. So that is this guy and this guy must just remain there. Now you can see A, B bar, C is remaining there, just like we had here A, B, C bar in the answer. Right? Now you can see here A, B, C bar is in the answer, right? So that guy must be there, right? Now if you factorize this red one and red one, yellow one and yellow one, green one and green one, you are going to get these things, right? So these small things you are going to get, right? So these small things you are going to get. I will just show you just one of those things. So let's factorize the green one and green one, right? So you can see A bar and C bar is there, right? A bar, C bar is there. You can just take it out. Then here you have the B bar, and here you have the A bar. Sorry. So what we took is green one, A bar, C bar. Now here we have the B, right? Here we have the B bar plus B. So that means B plus B bar is 1, A bar, C bar dot 1, something dot 1 is same thing. That is one of our rules. Therefore what we have is A bar, C bar. So from there we got A bar, C bar. Now here you can see we got A bar, C bar, right? So now you can see this is just like what we did here. When you multiply you must get this one, when you add this one, that is very straightforward. We don't know which one we have to, just like you break it 5 into 3 plus 2, we identified this one has to be duplicated, this one has to be duplicated. So that is why I just wrote it as this 3 times. So now you must have some sort of idea why we are marking these regions and stuff like that. We try to figure it out what is the best way to factorize, what is the best way to factorize. Then all of a sudden if you factorize that, anyway we are also going to get this simplest possible thing. The only thing is, without putting it to this kind of a graphical thing, we can't figure it out what is the best way to factorize. So the Kano is a very smart person, right? So he came up with this idea by thinking and thinking and thinking. He came up with this idea of putting it to the map, considering the it as a map and all those rules, and now all of a sudden we get the simplest possible thing. Now I hope you got why we are drawing a Kano map, right? It's so that you must have that kind of a mindset, right? So then only you are going to at least you are going to survive in this course and finish it, right? That kind of people are going to finish the course, right? So that means you are thinking little bit extra, try to figure it out why it is happening as well. Okay, so because when you go to the year 3 you must be like that. Okay, you must be like that. Okay, so now I hope you got it, right? Now you can't say why it is happening, I don't know, but something is happening and I get an answer. Now you must know exactly, just like this technique, by having these regions we get something like that. Okay, so again why we want to have big region is, when you have big regions you get smaller simple expressions. When you have small regions you get bigger expressions. What you need is simple expression, so less number of things. So that is why we go for bigger things, right? I will explain that also, right? So now here you can see so when you have big region like this, right, we get a very simple thing, right? When you have a small region you get big things. So that is why we want to go for big regions, right? And also when you go for big regions, lot of ones are already used, that means we have less number of expressions, right? So we want to make sure that we have less number of expressions and our expressions are small. So that is why we go for big regions, and that is why we ask you to overlap also. When you overlap you get big regions. So big regions means less number of things in your product, right? So likewise, why we are doing each and every rule, right? Each and every rule you must be able to justify. You must be able to justify. Then we say that you are doing this with some purpose, right? With some understanding. Okay, right? So now we are done with the sum of product Kano map. How to draw, not only how to draw the Kano map, because that you can learn from anyone, right? But why it is working, so that is what you want to know, right? So that is what we want to know. Then you are sort of a in the next level. Okay, right? Now you can do the same thing for product of sum as well. right? So we know that we have sum of product and product of sum. Only difference is all those rules are there. All those rules are there. Only thing is now when you are marking the regions, mark zeros, not ones. And also when you are getting the values, now you take it as sums rather than products. And again, here once you have to bar, zeros you have to keep it as it is. Remember earlier you take ones as it is, zeros you take it as bars. But now, because it's the other way, zeros you have to keep as it is, ones you have to bar, and it must be sum. And finally, those weak regions you have to product. So that is why we say product of sum, right? Product of sum. These are the sums. Now we are producting. Okay. Other than that, all the other rules are the same. Okay. Now I hope you got it. What is mean by Carnot map? Right. So we are done with the bulk of the stuff. Now let's do at least few fast paced questions. Right. So we will not be doing digital circuits today because 90% of the questions are coming from this part. This part. So let's do at least few fast paced questions now. Okay. Right. So right. So let's take 2019, let's say 2018 paper onwards. Right. So some of the questions are very easy. Let's try to do for one paper because you will see that almost every year you get the same sort of questions. Right. Consider the following Boolean function. Which of the following Boolean function provides simplified form of f? Now here you have to simplify because when you have very simple things like that, you don't have to go for Carnot map. Now you can see that this is a product of sum, right? So you don't have to go for Carnot map for this kind of one or two variables. You can just simplify. Now remember, now we can use one of the rules we use. Now remember, I gave you 23 rules. 23 rules. I am not going to use anything other than those 23 rules, right? So remember, now I know which rule I am going to use. I am going to use the final rule here, right? Final or the 23rd rule actually I am going to use because just by looking at this, I know this is like a plus b dot c plus d, right? A plus b dot c plus d. So that is my 23rd rule actually, if I remember correct. Right, so this one, right? A plus b dot c plus d, that is ac plus ad plus bc plus bd, right? So I am not going to use anything other than these 23 rules, right? And I know exactly why these 22 rules are working. I know exactly why this is happening, why this is happening. There is no mystery for me, right? There are no mysteries for me. I know why a plus a b say. I know why a plus a bar b is b a plus b, right? Each and everyone I can explain why it is happening, and therefore I can confidently use those things. So now I am going to use this one. I am going to use this one. So let's use this one, and also I am going to use few more if needed. Okay, right. So I am going to just simplify this because x plus y I can't simplify, x bar plus y I can't simplify. I don't see any other way. I am going to just simplify this the normal way now. So it is going to be x bar x x bar x plus x bar y, right, plus yx I can write it as xy because I know that AB is same as BA. I will just write xy plus y into y is yy, y dot y, right. Now let's see. Now I know that x dot x bar is, right, x dot x bar is what? 0 because a and belong to a and not belong to a is nothing, right? Belong to a at the same time not belong to a. So there is no cross section here, right? So that is phi. Phi means nothing means 0. This is 0 or false, right? It's a false, right? So therefore that is I put as 0, and also y dot y is we know why because a dot a is a, right? A intersection a is, now you can see everything is intersection a, right? That is y. Right? Now let's write this one as it is. If I want here also I can take y out, right? Because I know that x bar dot y is same as y dot x bar, right? X dot y is same as yx, so I will take that also y out. x bar plus x. Right? So this is y, this is 0. Okay. Now I know that x plus x bar is, right, a plus a bar is a plus a bar means, now I am not memorizing. A plus a bar means a o not a, right? A o not a. That means always you are correct. So it's something like you are saying. Someone will ask, have you had your breakfast? Someone will say, okay, I had breakfast or I didn't had breakfast. So that means you are always true, right? Your statement is, so that is what you learn in your logic as a tautology, right? So now you can say everything I can relate. A plus a bar is a tautology. So that is a true. That means 1. That is 1. So therefore that is 1. Right? That is 1. So now what I get is, so I will just delete this. Right? So now what I have is 0 plus y dot, this is 1 plus y, and I know that something dot 1 is a dot 1 is a, right? A dot 1 is a, so therefore y dot 1 is y, 0 plus y plus y, and I know that y plus y is y, that is 0 plus y, and I know that 0 plus y. If I can't remember 0 plus y, I go for my sets. 0 plus y is something like 5 union y. So that is belong, say forget about y, say a belong to a or belong to nothing, right? Belong to a or belong to nothing. So nothing has not going to give anything, but this union, either this line or that line or both line is going to work. So that is a, that is a. So therefore 0 plus y is y. 0 plus y is y. So therefore my final answer is y. My final answer is Y. Answer is D. Answer is D. 14. Answer is D. Right. So 0 plus A is a rule here. Right. 0 plus A is a one of the rule mentioned here. I am not memorizing. Right. 0 plus A is, you can see A plus 0 is A. Right. A plus A 0 is A. So my final answer is D. Right. D. 14. Answer is D. Now let's look at the answer. 14. Yes, 14 answer is D, right? 14 answer is D, right? So you can see you have to use all these rules, right? So, right? So without understanding, if you don't have any feeling about and logic or logic, you are going to have a really tough time. You are going to have a really tough time memorizing these things, right? When you try to memorize one thing, you are going to forget another thing, right? But using sets, I can anytime. I can verify. I can verify anything, right? Because sets is something I can, as humans, we are really familiar with, right? Because it's graphical thing. We are really good at understanding graphical things. We are really bad at understanding logical things. So conceptual thing. Logic is a conceptual thing, but set is a graphical thing. So that is why we ask you to, whenever you are in doubt, go for the sets, right? Go for the sets and come back to the logic, right? Come back to the logic. Now let's do another question. Right, so next question. Consider the following Boolean function. Which of the following Boolean function provides a simplified form of f? Right, simplified form of f. Now you can see it's not a sum of product or product of sum. It's completely sort of mixture of things, right? Now let's see how to do these kind of things. Of course, you can also try out. Right? So now you can see it is, and now you have to think in terms of blocks, right? So think in terms of blocks, think of it as a block. This is another thing, that is another thing. Okay. Now if you think it as a block, right? Now first you have to multiply these things. But some before try to multiply these things, see whether are there any familiar things. Now I can really see that I am really interested about this guy because I know that y plus y bar is what? Right? A plus a bar. A plus A bar is what? Now if I can't remember A plus A bar, I know that this is A union A complement. So that is belong to A or belong to A complement, that is E. That is E. E means in logic true. True means one. That I mean, if you forget it, right? If you forget it, you know that is one, right? So that is why I am very relaxed. In the exam, you must be very relaxed, right? Very relaxed. I can go to the exam without any burden because I know anytime I can figure it out. I know that this has an answer. If I can't remember, I know how to get it. Right now, this is one. Right. So if I start straight away, simplify, try to expand this, I am in big trouble. But now I found that okay, let's simplify this first. Then, if you look at these two as a block, that is something like x dot one. Then what is x dot one? X dot one is x. Right? If you can't figure it out, x dot one is x. You know that that is x intersection e. Right? It must belong to x at the same time belong to e. Of course, x must be within e. Therefore, it must be x. Right? Belong to e at the same time belong to x. So both lines are in the x. So therefore this is x. So therefore this dot one is this. If you take this as something like x, x dot one is x. Therefore now I can say x dot y dot this block that is x bar plus y. Right now I have come up with this. Now I can't. Now I have no option. Let's think it as a block now. Something like A. Now I can apply A dot B plus C is AB plus AC. I am going to use that. But I consider this as a block. Okay. That is x y x bar plus x y y. Right. Now I am really interested. I can always have these things because A dot B is same as B dot A, and then all of a sudden x dot x bar y. I will delete this plus, and I know that y dot y is y, so that is x y. Right. Then here we know that x dot x y is 0, 0 dot y plus x y. And I know that 0 dot y means uh, phi intersection y. So belong to nothing at the same time belong to y. If this one has nothing, it is always going to be phi or 0. This is 0 plus xy. And 0 plus xy means what? 0 plus xy is something like phi union something. Phi union something is what? This guy is not going to give you anything for you, so therefore it is going to be x. So that means xy. That is my answer. Answer is E. Answer is C. Now let's see whether the answer is correct. 15th one. Answer is C. Yes, 15th one answer is C. So that is how you do that, right? So if you have that understanding and your logic questions, you are going to really enjoy. Actually, if you enjoy maths, you are going to enjoy logic more than maths. After some time, you will see, okay, math, logic is much more enjoyable than maths. Okay, now let's move on to the third one. Consider the following Boolean expression. So it looks like really challenging one, right? Much more challenging because it's a very big one. Which of the following Boolean function provides simplified form of f? Right. So now let's see. Don't straight away start. See whether there are any patterns. See whether there are any patterns. And look at the answer also. Right. Look at the answer also. Now let's see. Now here you can see A plus B is common. Now don't just start right. Look to the patterns. Now I like to look at. I am interested about these two guys because you can see A plus B is there, and here also I think I see like A B bar plus A bar B, which is exclusive O, right? Because remember A exclusive O B is what? A B bar plus A bar B, but there are no exclusive O's here. But definitely I am interested about this one, therefore I am going to take A plus B out from there. And then what I got is C plus C bar and C plus C bar. And here I got A B bar plus A bar B. So I am not going to touch this. And here C plus C bar means we know 1. Right? If you are in doubt, that is C plus C bar is what? Belong to C, or union belong to, not belong to C. That is entire thing is true, or 1. That is 1. That is A plus B dot 1 plus AB bar plus A bar B. Right? Then something dot 1 is same. That is A plus B again. Right? A plus B plus AB bar plus A bar B. Still you can see the answer is simpler. Now I like to, now I want to do something like this. Right? Now if I take A, I'm going to factorize these two because I know that A plus B is same as B plus A, I can set these. If I take A out, that is 1 dot B bar. If I take here B out, now remember this is not B bar, I just draw it like to show that I am going to connect those two. If you take B here, that is 1 plus A bar, right? So now 1 plus B bar, 1 plus something is 1, right? Because in all logic, when something is true, answer is always true, or 1. So that is A dot 1 plus here B 1 plus something is always 1. Right? So finally what I got is A plus B because A dot 1 is A, right? B dot 1 is B. So what I got is A plus B. Right? So I hope I didn't make any mistake. So the answer is E for the 16. Yes, answer is C. Right? So now you can take another paper and you have to do by yourself. So I am going to do all the logic questions in this particular paper. Then it's up to you to take all the other logic other papers and do it because from the other part only one question or just two questions will be there, right? And you get about 6-7 questions from whatever we have covered today. Right. So now let's look at another question. So we did this one. So always look for the pattern. Don't jump into whatever from left to right. Right. Now this is the question. What is the minimum number of NAND gates required for the above Boolean function if it is to be implemented only using NAND gates? So today we discussed that there are two types of gates called universal gates. So there are two gates which can be considered as universal gates, that is NAND gates and NOR gates. So they ask you to, if you are implementing only using NAND gates, they ask how many NAND gates you need. Right? Again, what they ask is minimum number of gates, right? So not just number of NAND gates. Again, you are going to do some minimization, right? Minimum number of NAND gates, right? So we know that. So that is where you have to now remember how many NAND gates you need, right? So I will show from the now those things you have to remember actually. Right? We know that for an AND gate, right? You need two NAND gates, right? For AND gate, you need two NAND gates, right? For OR gate, you need three NAND gates, right? For NOT gate, you need one NAND gate, right? There are no XOR gates, right? For AND 2, for O3, right? For AND 2, for O3. Now let's look at it. For AND, right? For AND and 2, for O3, of course for NOT, you just need one, right? And now let's see if it is as it is, how many we need? For this end you need 2, for this end you need 2, for this end you need 2. For this O, if you want you can take it as just O having all. Now remember, when you have O, you can have 3 O's and you can just roll like that. That is convention, but reality is it is something like 2 O's. Then again, this one is O's, but if you want, you can just do it like that as convention. Okay, but reality is you need actually 2 O gates. You can do the same for the AND gate as well. Right? So I didn't cover all those things because within 2 hours, 3 hours, I can't do everything. So those things are covered in regular class only, right? Right. Now, okay, I deleted it, right? Okay. Right. So now say, oh, we need 3 at least, but in reality you need 6 actually, 3 and 3, but at least let's say 3 for these 3, these stuff 3, that means 3 plus 2 is 5, 7 and 9, right? 9. Now you can see even the 9 answer is also not there. Of course, in your paper, none of the answers can also be the case, but don't look at those things like that. When you are given this kind of question, every year you get this kind of question actually. This is what you are supposed to do. This is a technique, right? So this technique I am going to explain you. When you have this kind of a thing, we know that we don't like O gates. Why? O gates need more NAND gates. So that is our idea, right? So we know that O gates need 3, whereas AND gate need only 2, right? So let's again write it down. AND gate need 2, O gate need 3, NOT gate need 1. So we don't like O gates, right? Because O gates need more and more NAND gates. So therefore what we do is, this is always you are supposed to do, write it like this, bar bar. Because we know that A bar bar is A, therefore we have not changed it. Then apply De Morgan laws to this portion. Right? So then what will happen? A B bar, because De Morgan law can be applied to any number of things. Right? So that is why in the note it says, so everything, I am not using anything outside the note. Right? Right? Now you can see there are some dots, dot dot. That means A dot B dot C dot blah blah blah. So the De Morgan law can be used for any number of. So if you have A dot B dot C dot D bar, you can say A bar plus B bar plus C bar plus D bar, right? That is why we have set of dots. All the other rules you don't have dots, but here you have dots, right? Now let's write it down that. So therefore there is A B bar dot, right, dot, because De Morgan law, AC bar dot BC bar, right? So then you have this big bar here. Remember, we just expanded small lower bar, that is also there. Now you can see there are no O gates. Now this is a NAND gate. We can just use one NAND gate here, right? One NAND gate here. There's another NAND gate we can use because AC bar, another NAND gate, because for NAND gate you need just one NAND gate, right? Because NAND gate is a NAND gate. Then if you consider this as a 3 input one NAND gate, because it is something like A dot B dot C bar, so therefore that is also NAND gate. Whether it's a 2 or 3, we just say just one NAND gate, right? So for 2 also we say one NAND gate, for 3 also we say one NAND gate. In that case, we need another NAND gate, because these term, if you take like x dot y dot z bar, so here one, here one, here one, here another one, right? So therefore what we need, 1 2 3 4. So what we need is 4 NAND gates, right? So if you just apply as it is, you need, I think, 3, say this is 2 2 2 and 3, that is 2 4 6 9. But now what we need is only 4 NAND gates, right? So the answer is 4. Always when you get this kind of a thing, apply this rule, A bar bar, then apply the De Morgan law here, then you are done. So you can, by doing this, you can do any of the questions relate. Every year you get a question like this asking you how many NAND gates are needed. Always I will do this one. I will always get the answer, right? So I'm not going to do anything else, right? So the strategy is get rid of these plus marks, because they need more NAND gates. So then apply, when you apply the De Morgan law, your plus marks become dots, right? Your pluses become dots. That is good. That is good. And also not only the pluses become dots, it has that look and feature of an AND gate, right? Look and feature of an AND gate. A bar dot B bar, right? So this is NAND gate. A bar is an AND gate, right? So it will make your circuit more closer to the NAND gate. So the answer is B. So let's see what is the answer. Question 17, whether it's B. Yes, question 70 answer is B. Right. So now let's move to the next question. We'll do only this paper. So actually, if you can do one paper, you will see that's almost the same type of questions are everywhere. So next time we will do another paper and rest of the stuff. Okay, then we are done. And also you have to come up with all the questions that you have. Right. So let's look at another one. Yeah, just one more question. Right. The output of the Boolean function. This is that is very simple question. Right. So you don't need my help for that one. So you just see it says the output of the Boolean function is 0 when for what kind of a situation, right? For what kind of situation. So the best thing is apply this to this one and see whether you get 0, right? Again, be smart. So this is, I hope, AB bar, BC bar, AC bar, there, AB bar, BC bar. Now we know that if it is going to be 0, right, because this is 1 plus everyone has to be 0, everyone has to be 0. If you get at least 1 you can just eliminate that answer, right? So now see something like that. This is so here you have the C as 0. When it is 0, we don't mind what is the other one. When this is 0, right, always this guy is going to be 0. So when this guy is going to be 0, this guy is going to be 1, because 0 by is 1. When this guy is 1, definitely we don't care the other guys, it is going to be 1. So therefore I am eliminating. You can see I am using logic. I am not just substituting everywhere and doing it like a calculator. So I am working with very smart way. I know that when this is 0, this is going to be 0. That means this is 1. When this is 1, definitely regardless of these things, this is 1. But what they say is 0. This is out. So now I am going to look at another one. Here also C is 0. I'm not going to use it, right? So again, here you can see B is 0, but that is when B is 0, always the AND is 0, right? AND is 0. When AND is 0, this is 1. When this is 1, regardless of these things, this is 1, right? So this is not going to work. So that means if at least 1 is 0, because here you have AB, BC, AC, ABC. When at least 1 is 0, it is going to be 0. Now this is the only one I am going to pick now. And here both are 1. When both are 1, it is going to be 1, and its bar is 0. When both are 1, it is 0. When all are 0, only it is 0. So that is my answer. Now you can see I am not just substituting. I know how the AND logic work. I know how the OR logic work. So how does AND logic work? When all are 1, only 1. When all are true, only true. When at least false. When at least 0 is 0, answer is 0. How the OR logic work? When at least 1 is 1, it is 1. Or when at least 1 is true, it is true. When all are false or when all are 0, only your OR logic is going to be 0. So if you know those logics by not by memorizing, you have understood it, you can quickly get the answer. So my answer is E, right? 18 answer is C. Otherwise you will need more time. So those are the people who come and say that okay, paper is not difficult, so time is not enough. No, time is not enough, you are not smart enough, right? So whenever someone come and say time is not enough, what we know is you are not smart enough, right? So you have done things in a very dumb way, right? Very lengthy way, right? So you are not using the patterns, right? So now let's see the answer 18. Let's see whether it's a E. I hope I didn't make any mistakes. Yeah, 18 answer is C. Okay, so in that tier there are no Kano map questions or whatever, right? So let's do one question which has sort of Kano map, because from the next paper, because that year there are no other questions in logic. See whether we have any Kano map question or circuit question. Yes, there is a Kano map question. So let's do this one very quickly. Anyway, we will do the other part, because next time the lesson is going to be very short. We have more time for past papers. Okay. So this is a Carnot map question. Consider the following Carnot map. What is the most compact? That means the simplest Boolean function which represents. So you can see the answer is sum of product. Sum of product means we have to go for ones. Right? Go for ones. Now let's see without violating. Now this guy has given you the map itself. Therefore, we have less work. So, what is the biggest region? Are there any regions of 8? No regions of 8, right? No regions of 8. Then you have to look for, are there any regions of 4? Yes, there's a region of 4. Definitely, this is a region of 4. This is a region of 4. Are there any other regions of 4? You have to look for the regions of 4 first. Yes, there's a region of 4, right? Here you can see 1, 2, 3, 4, 5, 6, because these two are also next to this, but 6 we can't take because it must be 4, 8, etc. Therefore, I can't go for region of 6. There, but I can go for region of 4. What is that? These two, and these two. Because remember, these two are consecutive, right? Leftmost and the rightmost columns are consecutive. Now I have two more things remain. Of course, I can connect those two, right? Connect to those two. But if I can go for bigger region, that is better, because if I can go for 4, that is better. Of course, I can go for 4. Why? This and this one is consecutive, and this one and this one is consecutive. Therefore, this is the trickiest region. So these things are consecutive. So now I have another region of 4. This one, this one, this one, this one. Okay. So that is the trickiest thing you have to understand. Now let's quickly write the come up with the expression. So I will take this one. A, B, C, D. This is 0, 0, 0, 0. And this is 1, 0, 0, A, B, C, 1, 0, 0, 0. This guy is 1, 0, 1, 0. And this guy is 0, 0, 1, 0. 0, 0, 1, 0. You can see this guy is there, this guy is there. That is B bar, D bar. Right, I am done with that. So let's look at this region. Let me look at the picture here. So let's take that. A, B, C, D. 0, 0, 0, 0. 0, 0, 0, 1. 1, 0, 0, 0. And 1, 0, 0, 1. Right. So this is there, this is there. That is B bar, C bar. Now I have this region A, B, C, D, 0, 0, 0, 0, 0, 1, 0, 0, 1, 1, 0, 0, and 1, 0, 0, 0. This and this one, that is C bar, D bar. So my final expression is B bar, C bar plus B bar, D bar plus C bar, D bar. So B bar, C bar, B bar, C bar, B bar, D bar, C bar, D bar. Answer is A. Right? Answer is A. Now let's see if the answer is correct. 16A. Yes, 16 answer is A. Okay. So let's stop at this point. So the next time we have very small session, right? So we are going to cover everything. We are not going to right. So I did very slowly the previous things like sets and stuff, right? So we will be doing the small part, the different important circuit component. Then we will do for past papers in the next session, and we will finish. Okay. Right. So if you have any questions, you can ask all those questions next time, or you can put it into the WhatsApp. Or if you have any past paper question that you want me to discuss, we can have that also. So hopefully we will finish this. Not hopefully, we will finish this next time. Okay. Right. Thank you.